Assalamu alaikum, dear students. Now, this is going to be our lecture 4 for the course MTH 603. That is the first course on functional analysis. Of course, this would be for semester 6 of our integrated BSc MSc Mathematics. And let us start from where I left in the last lecture. That was, we proved Hahn-Banach theorem. Now, it has been a long time because there was a problem with my recording device. That's my mobile phone. Now I think I have sorted it out. So let's start from where we left. Now, as we know, the Hahn-Banach theorem states that if X is a normal linear space and Y is a subspace of X, and F is a bounded linear functional defined on Y, then it can be extended to a bounded linear functional defined on the whole space such that norm of f is equal to norm of f naught. We have discussed it in almost 3 lectures. We finished it. Now let's come to, this is a very important theorem in functional analysis, and it has a lot of important consequences. Now, one of the consequences of this theorem, of this result, would be this theorem. Now let me write down the statement. That is, if X is again a normal linear space, I write n less in short, and it has got some non-zero vector inside it. Now say x naught is some non-zero vector belonging to x, then I can find a functional, and if there exists some f naught belonging to x star, that means f naught is a mapping, let me remind you, from x to the scalar field k, such that f is linear and bounded, which means basically linear and continuous. Okay, so if we have, then there exists an f naught belonging to the x star, that means a functional defined on x, such that I can choose the value of that functional. That's important. Add that vector to be the norm of x naught, and also norm of f naught is equal to 1. Now this is again a very simple consequence of what we have already done, the Hahn-Banach theorem, and its proof is again pretty simple. You just look at your notes. So, but I will just give an outline, but you can do it yourself. So what we do, I take this non-zero vector and I take all its scalar multiples. So I let my y to be all scalar multiples of this non-zero vector. Then y is a subspace. Of course, it's a linear subspace of x that is spanned by this single vector x naught. It's a one-dimensional subspace of x, nevertheless a subspace, right? So then, now this is a one-dimensional subspace of x, this y, and I define a function f from y to k by f of y is equal to, of course, y is of the type, any vector of this subspace y is of the type some alpha times x naught. I define it to be alpha times norm of x naught. Now this is a number, alpha is a number, so it is a number, so it is indeed a map from y to k. Now it's again very easy to show that, if you look at your notes, that it is linear and bounded functional. Now linear and bounded, now you can just check it. Now if we checked it, so if you have two vectors y1 and y2 belonging to y, that means y1 would be some scalar multiple of x naught and y2 would be some scalar multiple of some other scalar multiple of x naught, right? So that means f of y1 plus y naught would be essentially f of alpha 1 plus alpha 2 into x naught. And if I apply my formula, this thing, now it should be equal to, according to this formula, alpha 1 plus alpha 2 into norm of x naught, and that is nothing but alpha 1 norm of x naught plus alpha 2 norm of x naught, because scalar multiple are just distributive law of numbers, now which is nothing but f of y1, of course it is y2, f of y1 plus f of 2. Similarly, for scalar multiplication, you can check it is linear and it's also continuous, right? Because f of y in mod is equal to mod of alpha times norm of x naught, which is nothing but mod of alpha into norm of x naught. And if you remember the properties of norm, this is this, which is nothing but norm of y. So modulus of f of y is equal to norm of y, which means it is linear. Not only that, it also shows that norm of f is equal to 1. But what do we have to show? We have to show that a functional defined on the whole space of x. We have just f that is defined on this subspace is one-dimensional subspace of x. So if I continue with it, so now I apply my Hahn-Banach theorem. So I indeed have now f. Now it means that f belongs to y star, and y is a subspace of x. Therefore, by Hahn-Banach theorem, there would exist an f naught belonging to whole space and a bounded linear map defined on the all of the space of x, such that f naught when restricted to y is the same as f, and norm of f naught is equal to norm of f, which we have already shown to be 1. So one part is clear, that norm of f naught has to be 1 by our Hahn-Banach theorem. Another part is f naught at x naught. So yes, f naught at x naught. Now x naught belongs to y, right? So therefore f naught at x naught should be the same as f of x naught, which is the same as f of 1 into x naught, which is the same as 1 into norm of x naught, of course. So you have f naught of x naught is equal to norm of x naught. So we sometimes say that this functional attains the norm of its argument of something in the domain. So that proves this theorem with the help of Hahn-Banach theorem. It was pretty easy actually. Similarly, I can have another corollary, that is, as a corollary of this, that what we call in topological language separation of points. So we say that x star separates points in x. Now remember that this is a collection of functions defined on x that are scalar valued, linear and bounded. Now what we are going to say, this collection of functions separates points on x. By that we mean, if you have got xy belonging to x such that x is not equal to y, then there exists f belonging to this function which would separate these two distinct points. And I can find f belonging to x star such that f of x is not equal to f of y. Again, very obvious. Okay, I'll leave it to you. It's simple. And if you have x not x sort of not equal x not equal to y, it would imply that x minus y cannot be equal to 0. Then apply previous theorem to this vector, because now this is a non-zero vector of our x, which is a normal linear space. You apply the previous theorem and it's done. Okay, now we define something now, an important definition, which is obvious, again very simple. So if you have x and y, two normed linear spaces, and they are both vector spaces with a norm defined on them, then we say a mapping. If I have a mapping T from x to y, that's a one-to-one linear transformation. It's linear. It preserves the linear vector space structure such that it also preserves the norm, and a norm of Tx is the same as norm of x for all x belonging to x. We say it's an isometric isomorphism, right? You have a map that is 1 1, that's onto, that's a linear transformation, of course, huh? And and we say of course it's a what I said, isometric isomorphism, and if it is onto, also if it is a bijection, then we say x is isometrically, in case t is onto, we say x is, because then t of x would be the same as y, we say x is isometrically isomorphic to y. Of course, by that we mean they are pretty much identical as normal linear spaces, because it preserves the topological metric structure, the norm structure, as well as the algebraic structure. Okay, so that was just a definition. Now, after that, we can talk of another sort of a consequence or a corollary of this Hahn-Banach theorem. So let us do another theorem. It's given in the notes again. If y is a closed, now closed is important, closed linear subspace of a normal linear space X, such that, now remember this, such that x naught belongs to x minus y, and x naught belongs to x but outside y, then there exists f naught belonging to x star. Now it's important, again it's a very important corollary, an important consequence of Hahn-Banach theorem. F naught belonging to x star such that f naught sends every vector inside y to 0, which we write as f naught, the whole f naught kills y, rather it sends every vector to the 0, and but this vector, this particular vector that we chose outside of y, it is not sent to 0. Now this is one of the important structure theorems that we can use to study normal linear spaces. Now come to the proof. Again, this is very easy. Now what we define T, a mapping from x to x by y, what we call, this is the quotient space, you remember this, huh? Quotient space, by that we mean the space of all cosets, and it's the space of the type x plus y, such that x belongs to x, and we know that it's a vector space. Okay, we also have done in the class that this is a normal linear space if y is closed, and I'm choosing y to be closed, so it's a normal linear space with norm of the coset x plus this capital Y. Norm of the coset is infimum of the norm of x plus this small y, where y ranges over all the elements of this subspace Y. Okay, now this is a map T from x, and if it is the natural embedding, the canonical map that you know from your algebra courses, we define it to be T of x as just x plus y. Now I leave it to as a home assignment that T is a bounded linear map. A bounded linear map, linear is obvious. Oh, actually that's also obvious if you look at this formula for the coset norm, so it should be pretty straightforward. So it's a bounded linear map T from the normal linear space x to x by y, and it is normed by this definition of the coset norm, and of course our map is that natural embedding, what you call it, canonical map, whatever, embedding to near, but it's the canonical map, sorry, canonical map. Okay, now then now T is a, now look at this map. Now you must know that if I take T of y, it would be y plus y. Means if y belongs to this subspace, T of y is y plus y. That's equal to y. But remember this capital Y, if y belongs to this y, then y plus y would be y. Just simple algebraic thing. It's a vector space. Okay, but this y is the zero element of x by y. Again, from algebra, you know that the zero element, the additive identity of x by y is the y coset, because it is 0 plus y. Okay, now it means that t of y is equal to 0. By 0 I mean the additive identity of x by y, matlab for all y belonging to y. Okay, and also t of x naught, t of x naught is equal to x naught plus y, cannot be equal to y. We know that this is y plus y is equal to y if and only if y belongs to y, and since x naught does not belong to y, therefore x plus x naught plus y is not equal to y, right? So this cannot be equal to 0, and t of x naught is not equal to the additive identity of x by y, which I can call 0, no issues. So what do I have? I have got a linear map from x to x by y, right? And I have got a vector, a non-zero vector, a vector x naught plus y. Now if I look at this, x by y is a normal linear space. Now keep this in mind. Now look at x by y. It's a normal linear space with a non-zero vector. It has a non-zero vector. That's x naught plus y, which is not equal to 0. By 0, it is not the additive identity, right? So by previous theorem, there exists f belonging to the dual of x by y such that f of x naught plus y is equal to norm of x naught plus y. Look at the previous theorem. There it was x naught, but here our vectors are cosets. Now, which is not equal to 0. Because norm of a non-zero vector cannot be 0, because x naught plus y is a non-zero vector. Okay, by this norm, it is actually the norm of x by y, right? So I used Hahn-Banach theorem. Now what I do, so now I have got a map from x to x by y, that's t. Then I have a map which, because f belongs to the dual of x by y ka star, which by Hahn-Banach theorem exists with the properties that I have, with the given properties, of course. Then, and this goes to k. Now if I compose this thing, what is this? This is f composition t. It is the composition of two linear continuous, two bounded linear operators. Therefore, it is a bounded linear map, right? So I call it f naught. Okay, so f naught then belongs to x star, right? Okay, and f naught of x must be equal to f composition t of x, which would be equal to f of t of x, right? And so this is my map. This is a functional that I was looking for, that I have to show the existence of. And if I look at f naught of y, f naught of y would be f of t of y, but t of y is 0 as done previously, so it would be f of 0. But f is a linear map, it would always send 0 to 0, so this would be 0. Our first property is met. Now this is true for all y belonging to y, of course. And furthermore, if I look at f naught at x naught, it would be f of t of x naught, which is equal to f of x naught plus y, right? But f of x naught plus y is equal to norm of x naught plus y, again by our previous theorem. So this cannot be equal to 0. So QED, we got the result. Okay, now we turn to what we had done earlier, and I promised you in the class the converse of this theorem is also true. We have shown that if x and y are normal linear spaces, if I take all the collection of all bounded linear operators p, x, y, what does this mean? This means all the maps from x to y, let me denote them by t, such that t is linear and continuous. Now we had shown that this is a normal linear space. under the sup norm. The norm of t was defined to be supremum norm x equal to 1 norm of t of x. So this was the definition of the norm in the space, and we had proved there if y is complete, if y is a Banach space, then so is bxy. Now I had told you that we don't have the machinery to prove that at that time, that if bxy is complete, it would also imply that y is complete. So now the time has come to prove that. Okay, so let's do this theorem that says if x and y are normed linear spaces and if bxy is a Banach space, is complete, then so is y. Let me see what is the time. Okay, we can continue for some time. Now proof, we are given that bxy is complete, we have to show that y is complete. Okay, now let's start. Let f belong to x star. That means it's a bounded linear map from x to the scalar field such that it is a non-zero map and it's not the zero element. Then for each y belonging to y, we define the map t sub y of x to be f of x into y. Okay, now what is this? This is a scalar, this is a vector inside y. So this is scalar into some vector inside y, therefore this thing belongs to y. And of course x belongs to x. So t sub y for each y, each choice of y is a map from x to y. Furthermore, ty of x, if I take its norm, it's of course linear because f is linear. That can be easily verified. So it is norm of f of x into y, which by the definition of the norm would be mod of f of x into norm of y, which is less than equal to, because f is a bounded linear map, norm of f into norm of x into norm of y. So which implies that ty belongs to x star. That's obvious. Just this is your k of the definition of the bounded linear map. Okay, now so that means ty, ty is a map from x to y, so ty must belong to, it's a bounded linear map from x to y, so it belongs to for all y belonging to y as per our definition. Now I define f from y to bxy. That's obvious how we are going to define. I define this capital F of y to be t sub y. We know that for every y here there belongs something here, so we just join them via a functional formula. It defines a function, in other words. Okay, now look what I have now. If I look at the norm of t of y, by our definition there is a definition of a norm inside bxy. What is that? That is supremum norm x equal to 1 mod of ty of x, ty of x, of course, because no, it has to be norm of ty of x, which is equal to supremum over norm x less equal to 1 or less than equal to 1. They are the same, so that is fx into y as per our definition, which would be less than equal to, applying the formula that we did here, so it is less than equal to supremum over norm x equal to 1 norm of f into norm of x into norm of y, and but I am taking the supremum over norm x equal to 1, so it should imply that norm of ty is less than equal to norm of f into norm of y. Now keep that in mind. So we continue. Now let's call this, let's name this, call this star. After that, we have to show that y is complete. So we have to show that every Cauchy sequence converges inside Y. Now let's take a Cauchy sequence. Yn be a Cauchy sequence in Y, then since norm of t sub yn minus, now if y is in Y, there is a functional t sub yn in bxy. So tym is less than equal to norm of f into norm of yn minus ym. Now that's just as per our star equation, right? Now look at this. So what we do, now we know that this is a Cauchy sequence. Cauchy sequence means this thing becomes arbitrarily small as nm approaches infinity, but this is less than equal to this. That means this thing on the left hand side also becomes arbitrarily small as nm become very, very large. So which implies that Tyn is a Cauchy sequence in bxy, but by our supposition bxy is complete. So it implies that there must exist a functional operator, a bounded linear operator inside bxy such that t of yn converges to that. Let's call that S. It means there exists some S belonging to bxy such that Tyn converges to S in norm. So now what we do, we choose an x0 belonging to x such that f of x0 is equal to 1. We can always do that as long as space is not trivial. If it was a trivial space, then basically there is nothing to prove, honestly. But if x0, if it is a non-zero, if you have a non-zero vector, then you can always send it to its norm, vagara, vagara. So we can always, but f, remember that, what's f? F is a functional. So I can choose f of x0 to be 1. If it was not, I would divide it by the same scalar, the vector divide by the n. I can choose x0 to be f of x0, provided that f of x0 is not equal to 0, which I know is not the case, because we know that f, our choice for f was that f is not a zero functional. It doesn't send everything to 0. Okay, so there is no problem in assuming this, right? And let y be equal to s of x0. Now s is a mapping from x to y. So it would send, now x0 belongs to x, so it would send this vector to y. So let's call it small y, because it lives in capital Y. That's our way of doing things. Now look at this, norm of yn minus y. If I look at this, this would be norm of, now I can just, what do you call it, swap it, because norm would not be affected. So I write, in place of y, I write s of x0. Then I write f of x0 into yn. Why? Because f of x0 is just 1, right? So, but this can be then written as per our definition, norm of s of x0 minus ty sub n of x0. Now that is the definition of our map T. Okay? Now which would be by the algebra, because it's a vector space and the operations are defined pointwise, so this would be nothing but s y sub n applied to x0, which is less than or equal to, because it's after all a bounded linear map, so it would be less than equal to s minus t y sub n norm into norm of x0. Now we know that this ty sub n converges to s. It means this becomes very, very small as n approaches infinity, but this is less than equal to this, which means that if t of yn converges to s, then yn must converge to y. So I have got yn converging to some vector y belonging to y. So yn was an arbitrary Cauchy sequence, which I know now. And I picked a arbitrary Cauchy sequence which I showed that it Convergence inside Y would imply Y is a Banach space, a complete normal linear space. So that finishes this lecture.